Hey, this is Brock Lemires, and in this video we're going to look at using the ultrasonic sensor, the HCSR04, and controlling it with the Arduino single board computer. All right, so what is an ultrasonic sensor? Okay, so sonic refers to sound, which is a pressure wave, so that's what we create with our voice and we can hear with our ears. But human ears can only hear sound that's about from 20 hertz up to about 20 kilohertz. So 20 hertz is like low bass, and then 20 kilohertz is really, really high pitch. Okay. Ultrasonic means that the sound is at a frequency that's higher than what we can hear, but it's still there. Okay. And so for sensors, people usually use around 40 kilohertz. Okay. So this is something where the sound is there, it's traveling around, but humans can't hear it. And it's still there, and it still travels at the same speed, which is 343 meters per second in dry air, even though we can't hear it. Okay, so what an ultrasonic sensor does is they usually have two components. One is a transmitter and one's a receiver. And the transmitter will actually send out an ultrasonic pulse, and then it will travel out and it will bounce off or echo off of a surface, and it will come back and be received by a receiving component. So one is the sender, one is the echo receiver. And then what you do is you can actually calculate the round trip time to determine how far away the object was. So if you know the velocity that it travels and you know that it's going to go down and back, you can take the velocity and the round trip time and you can calculate the distance. So that's what we're really doing, is you send a sound pulse and then you measure the echo. Okay, so the very common one that you see on these little robots, these starter robots, is the HCSR04. Okay, and so what it does is it's a 4-pin device. It's got power and ground, and then it's got a transmit, or sometimes they call it a chirp, and you send basically a digital signal to it, and it will send out a series of ultrasonic bursts, and then it will receive them on the other receiver. So what's cool about this is that there's actually circuitry on the little sensor so that it'll convert the round trip time into a pulse. So this is a timing waveform of what actually happens on here. So to control it, what you do is you send a trigger signal to the transmitter, and it's a digital signal. So it just has to be greater than 10 microseconds. So from an Arduino, you just do like a digital out, and we wouldn't even go down to 10 microseconds. We'll do like 2 milliseconds. So something that's really easy to create using Arduino. Once we do that, the ultrasonic sensor will automatically send out a series of 8 sonic bursts. And you go, why would it do 8? Well, it's got circuitry on there to kind of make sure that it's sending something that's very distinct, so that it doesn't receive just a random piece of sound and think that that's what the signal was. So it basically has all this signal processing chip or circuitry on it, so that it sends out 8, and then it looks for those 8. And then what it does is it actually will return a pulse, and this is just a 0 to 5-volt pulse that you can read with a digital input pin on the Arduino, and it basically will tell you the duration of time from when it's sent to when the pulse was received, or the pulses were received. And so that's all it is. It's actually really simple to do, and you can do a little math to try to figure out how this works. Okay, so here's what we're going to do on ours. So this is a picture of the HCSR04 ultrasonic sensor. You can see it's got 4 pins. We want to connect +5 to VCC, ground to ground, and then we have a trigger signal and an echo signal. And what we're going to do is we're going to use the breadboard shield for the Arduino, and we'll wire the trigger signal to pin 13, and then we'll just drive to pin 13 a digital write, and then we'll receive the echo on pin 12, and then we can actually grab +5 from the Arduino shield down here on this bank, and then ground right here. So let's wire this up, and then let's write a program and kind of measure some of the signals to see if we understand what's going on. Okay, so here is our little HCSR04 ultrasonic sensor, and here's our Arduino. And so what I'm going to do is I'm going to wire this up. First thing I'm going to do is I'm going to grab one of these cables that came with the robot kit, and I'm going to go ahead and plug it into the back, and it's keyed so it can only go in one way. And then what I want to do is I want to like wire this into the Arduino, but I want to wire it in so that I can observe some of the signals with an oscilloscope. So what I'm going to do is I'm going to come over and I'm going to wire up power and ground using these male to male connector or wires that come in your kit or that we gave you. And so let's do red for VCC, and I can kind of look at the silk screen right there and figure out which one's VCC. So I got VCC over here, and that'll go right into this power bank right there. And then I'll do brown for ground, and that's going to be on this one right here. Nice to kind of line it up like that. And I see, okay, so I got ground there. And then what I want to do is I want to grab the echo. We'll do green for that one. So green is right here. And then that is going to go into pin 12. And so, but I'm not going to go right into 12. What I'm going to do is I'm going to go into the breadboard so that I can then jumper it into 12. And then what I'll do is I'll attach an oscilloscope to it too. Okay, and then this is the trigger, and this trigger line is going to be what we send. Okay, so we're going to send a digital high out on that one to start the transmission. So what I have here is it's wired up right there. Life is good. And then what I want to do is I want to then connect to the Arduino. So I go ahead and go to pin, make sure I got this, pin 12, and you can kind of line it up like this. One thing I'll do is just make sure I got it in the right slot as I'll go like this with a screwdriver, and it's like, okay, I got it. That's pin 2. That's 12, except that 12 is going to be green. So let's put 12 in green right there. Use my screwdriver to make sure it's in the right. Okay, there we go. And then this one will be 13. So then when I bring this around, what I can do is I can then say, okay, green into green, and then yellow into yellow. And it's obvious that this is, I could have gone straight from here to here, but the reason I'm doing that is I want to look at this with an oscilloscope so I can actually see what's happening. Okay, so in order to do an oscilloscope measurement, what I'm going to do is I'm going to bring out a little analog discovery, and what I'm going to do here is I'm going to use these little pins that I have. So this was a pin header strip that I just cut apart, and let me get you back on the screen there. Okay, so what I'm going to do is I'm going to take these and I'll plug them into the breadboard shield where I need to pick up stuff. So the first thing I want to pick up is ground. So I'll get ground there, pick up ground there, or the analog discovery. And then what I want to do is pick up these two pins right here so I can see like what goes out and what comes in. Okay, so I come right in the middle there, and then I have those pins on there, and then I'm going to hook the oscilloscope channel 1 to the trigger, which is the yellow, pin 13, and then I'll connect oscilloscope channel 2 to the echo, and that's what comes back, and that's what's actually coming out of the HC, or excuse me, yeah, the ultrasonic sensor. So it's not actually the sound that we see, it's the process signal that we see. Okay, so that's all the stuff that we have in there. So I should be able to actually write a program for this and then see something happening. So let's plug that guy in, and then let's take a look. Okay. All right. So I come back over here, and what I want to do is I'm going to bring up an Arduino sketch. Okay. So I'll go ahead and do this. All right. So then last time we kind of looked at these pound defines in order to make our code a little bit more readable. So let's do a couple of those. All right. First of all, let's save this little fella. So let's go ahead and save it. And what we can do is we can come along and go into, I'm working on the desktop here. So desktop, one-on-one sketches, and I'll do 06 underscore ultrasonic sensor, and I'll do 2 because I was playing around with it before. Okay, so I got that little dude, and that actually created, no, that's saved. All right, so here we go. So we got our Arduino sketch. So let's do a pound define, and let's create a constant that's called trig pin, or actually what's called just a macro. It's just a replacement. So anytime in your program you type trig pin, what'll happen is that will replace it with the number 13. So this is pin 13 where where trigger, and this comes from. Okay, and then let's do pound define, and let's do echo pin, and this is going to be pin 12 where we wired it up. So this is pin 12 where input echo, and I'll say comes in. Okay. All right. So now we're sitting there, and let's go ahead and see if we can even get a pulse to be generated before we do any calculations. So let's do serial begin 9600, and that's the bit rate that will send information up to the serial monitor. And then the first thing I need to do is I need to configure both of these pins to be either an input or an output. Now they're both digital pins, pin 13 and 12. And so what I do is I do pin mode, and then I give it the pin number. But since I did a pound define, I can do trig pin, and then I do output. Okay, so basically what this does is it says make trig pin and output. Now that comment is kind of silly because you can always read that statement and know that that's what I'm doing. But now let's do echo pin, and let's say that's going to be an input. So that's where we read this pulse. So now I come over here and I go make echo pin and input. All right. So, okay, got it. All right. So now I come down here, and let's first start by just simply creating a pulse, and then let's measure it with an oscilloscope and see what happens with this sensor. So the first thing I'm going to do is I'm going to do a digital write, and I'm going to send to the trig pin a low. So I know that it goes low. And then what I want to do is I want to do a delay microseconds, and then I'll do 2. Okay, so then I do that too. So it goes low for 2. Now what I want to do is I want to do a digital write to the trig pin in order to go high and start. So that basically what this does is it is the high part of the pulse, and I want to delay microseconds 10. Okay, and then what I want to do is take it low again. Okay, so then what I'm going to do is digital write trig pin, and I go low again, and then I do a delay microseconds seconds 2, and then I'm done. Okay, now you look at that. Basically what I do is I go make sure you're low, then go high for 10 microseconds, and then go low. And if you're wondering why I'm doing that, I'm trying to generate this. I'm trying to generate a pulse that goes high, and that will start the ultrasonic sensor. It's basically its burst. Okay. So now at this point, what I can do is I can actually save this, and we'll go ahead and download it and see if I can see that pulse come out. So let's see. Let's get our little screwage here. So we got digital. Okay. Let's download that. And then what we'll do is we'll bring up the oscilloscope, and we'll take a measurement of it. Okay. Let's see if we got it. Not using the serial monitor yet. So this is running, okay? And I should have printed something, but let's just go look at it with the oscilloscope. So now I got the oscilloscope right here. I got my analog waveforms. I've already wired it up, and I've already attached it. So I'm going to go in and I'm going to grab the scope tool, and I'll go ahead and run, okay? All right, so I got lots of stuff going on here. So let me zoom in. And I got so much stuff going on, it's like, oh my gosh. So what I want to do here is I want to grab the trigger, and I want to trigger off 1 so I can kind of see my pulses. What I have done here though is I can tell right away if I stop. I go high for my 10 microseconds, and then I go low for 2, low for 2. This doesn't work very well because what I need to do is I need to give it delay so that the signals can actually come back as they bounce. Okay. And what I mean by that is if I look at this, I do this, and then what I was doing is since I didn't delay long enough, I would send a pulse right away. And so it wouldn't even give time for this thing to happen. So let me put a delay in there, and then let's compile. I'll put a delay of 1/4 of a second or 250 milliseconds. Okay. And so now I do that. And now let's go back to here and let's run and see what happens. Okay. So this is looking a little bit better. I see something there. Oh, baby. Okay, so look at this. Here is my pulse, okay? And what I'll do is I'll move it kind of over here. And then, let's see, keep moving it over. And then I start to see the return pulse, okay? So orange is channel 1, that's my trigger signal. And then blue is what gets returned. And so the pulse width on here, what I did is I went up here and I hit track, quick measure on pulse. And I put this in here. And basically now what I'm looking at is I have this pulse will change based upon how far away an object is. Okay, so let me adjust the camera so you can see it a little bit better, but I'm basically taking this and I'm getting close to my hand, and the pulse gets smaller, and then I go further away, and it gets a little bigger and a little bit bigger and a little bit bigger. Now, one of the challenges with ultrasonic is that when the surface is not flat, the sound bounces all over. So it's like it's kind of going through my fingers, all that sort of stuff. So let me get something that's flat. So here's like a notebook, and let me put that right there. And then let's do this. And so you can see it's a little bit more steady, and then I go back and it gets wider and wider and wider and wider, or wider and wider, and it looks pretty good. Okay. So let's see if we're even remotely close to some of the calculations that we did. So let me put a little tape measure there. And you know, this is like a foot about over here, and then I'll put this book right here. And so as we come over here, you know, what is it doing? Let's get our little measurement on there. So if I pull it back to like all the way over to here, I mean, you're looking at, you know, there it is. It's about 1.7, 1.8, you know, it's almost 2 milliseconds a foot. Okay. So it's like, okay, let's come over here, and then, okay, so anyway, it's doing what we wanted it to do. All right. So now let's think about, let me try to balance that thing so we can keep it there. And okay, so now let's think about how we can bring in this pulse width information into the Arduino. All right, so one of the things that we think about is speed of sound is 343 meters per second. That's 34,300 centimeters a second. So that's 767 miles per hour, just roughly 1,125 feet per second. So it's about a foot per meter per millisecond, okay? So if you're 1 foot away from an object, you're gonna get about 2 milliseconds, okay? And that was what I was just showing you right there. Now, the Arduino actually has a function that's called pulse in, and this is built into Arduino, and it's really cool. It's used to measure the time that a pulse is either high or low. And that's really handy for what we're doing, because that's exactly what the ultrasonic sound sensor gives us. So what you do is you can use this function on a digital pin, and value, you can either give it high or low, and it tells it what to measure. So if you want to measure how long a signal is high, you give the value argument high, or if you want to measure how long it's low, you give the argument low. So we're going to measure obviously high. And so what we can do is we can say pulse in on the echo pin and measure how long it's high. Now the trick here is that this function will return an integer. So we need to set up a variable of type integer, and we'll call it duration. And that's how we'll actually read in the duration. Okay, so let's go back and let's do that. So now what I've got is I'm going to go back up into above my void setup. And what I'm going to do is I'm going to create a variable called duration. Okay, and this will hold pulse duration in microseconds. So microseconds is really important. That's what is returned from the pulse in function. So now when I come down here, what I do is after I send that pulse, what I do is I wait for it to return, and I can actually do the delay here, or I can come down here and say, actually, no, I need to I need to tell it to measure this right away, because I don't want to wait until the thing goes by. So I want to do duration equals, and I use this function pulse in, and then I say echo pin, and I say high. Okay, so now that's going to grab the information. All right, life is good. And then let's just wait until it completes. And then after that, I'm going to do serial.print, and then I'll do duration. Okay, and we'll just print this out as an integer, and it's going to be in microseconds. So let's do a serial.print, and then let's go space microseconds, and then a return, and then let's go ahead and do that. And after the duration argument actually finishes, you can then, let's cut that. I'll put that right there, and I'll do delay. Okay, so what this is going to do is basically print out the information to the serial monitor, and we can actually see what the Arduino thinks the duration is relative to the actual measurement that we have. Okay, so it's compiling in there, it's running, so let's bring up the serial monitor, and let's see if it's going. Okay, so we got 2,000 microseconds, okay, whatever. What are we comparing that to? So I'm going to get the oscilloscope on here, and I put that right here, and I'm going to have the pulse on there. Notice it's really kind of hard to see. It's over to the right. It's really small. It says 2.1 milliseconds. That's about what we're getting there. So now let's come back to our ultrasonic sensor and let's move this in. Look at what it's doing. 500 microseconds about. If I move this measurement tool over there, yeah, it's about 400. It's about 500 microseconds. So this thing is actually measuring a pretty accurate pulse width. And so when I get back to here, it's like that's where it's about a millisecond. And you're like, where did that foot per millisecond thing go? Well, remember the sound has to travel down and back. Okay, so this is working. So I can actually measure a pulse with this pulse in function. So now the final part of this though is let's convert this into distance, because that's really what's interesting to us. So what I'm going to do is I'm going to come back up to here and I'm going to go int and I'm going to go distance, and this will be a variable that will hold distance from sensor to object in centimeters. Okay, now centimeters is really important because we're going to do the conversion. Since we're really close to stuff, we want to do the conversion into centimeters. Okay, so into something that's small. We don't want to do meters because it would be really small. So now what I'm going to do is I'm going to go distance equals, and then I need to think about this. So let's go back to this and let's think about how we can convert the pulse width into centimeters. So remember, the speed of sound travels at 34,300 centimeters per second. But the pulse in function returns an integer that's already in microseconds. So we have to apply that microseconds to the 34,300 centimeters in order to convert everything so that we get just a number that is the integer number of centimeters that you are far away. And then what we do is you just take the duration of time, you got to divide it by 2 because it goes down and back, and then you multiply it by 0.0343, and that comes by applying the microsecond unit to this to just give us centimeters. So that's all we really need to do. So let's go do that in code and see if we can actually get it to work. So I'm going to go 0.0343 multiplied by, and I'm going to say duration divided by 2, and that duration is obviously was calculated right here. Okay, and now let's print it in, let's print it like duration first, and then let's print the distance. So I'm going to say, actually, let me do this. I've got duration in microseconds. Instead of doing microseconds and then a return, let me do a tab, and then let's do serial print, and then I'm going to do distance. Okay, and now this time I'm going to go serial.print, and now let's print the text centimeter, and then that time we can do new line. Okay, so now what this should print is the same thing, but it's actually going to give us a distance. So now let's fire this up and let's see how accurate we are. So it's going to compile, it's going to go down there, and we got a whole lot of stuff here that's going on. So I do that, and now it starts running. It says 9, oh, look at that. It says 9 centimeters. So first and foremost, let's get our waveform up so that we can verify that this thing's going. And now here we are down here with our sensor, and we got our ruler right here, and the centimeters are up here. So it's backwards from the camera view, but here's 10 right here from the notebook. So if I go to 10, oh my God, look how close it is. 10 centimeters. And then if I go up to here to about 5, it's like there's 5 centimeters. Let's go back here to about 20 centimeters, 17 centimeters, and then 20 centimeters. It starts getting less and less accurate the further back you get. And it actually kind of falls apart once you get too close. Although in this situation, like I'm right up against it and it doesn't know what to do. So it works from like 2 centimeters back. It claims to work out to like 10 meters, but it doesn't at all because the sound is like spreading as you go. But this is really accurate out from about 2 centimeters out to about 20 centimeters. And that's really cool because that's about if for a robot that's about a foot long, that's about where you want to look out and say, hey, we're going to run into something. And so you did it. That is it. That is how you can use the ultrasonic sensor in order to measure the distance to an object. Nice job, and we'll see you.